Okay, so let me start by asking first if there are any questions or suggestions. Yeah.
I don't know how to do problem 10.
Problem 10?
Also problem
And what other problem?
9. Problem 9.
9?
I had a problem producing floating point values within a range. I could produce like integer values, but I didn't know how to produce like random floating point values.
I think we looked at that last time. And let me see where we had that. Right there. Look at this line 17. This one here. So we're printing, here we're printing k random values between 0 and 1. And so let's parse this line here. So we're declaring a variable x, and we're setting it equal to the result of this expression. And this expression rand returns a number between 0 and int max. Int max is a constant that's defined in here, C limits, which gives you the largest possible int in the system. And rand returns an int. So we take whatever rand returns to us. Oh, but before we do the division, we need to cast the int to a double. Otherwise, the compiler thinks we want integer division. So we'll lose the fractional component, which would always produce a 0. This expression here, rand divided by int max, always produces a 0, unless rand happens to return int max. So in the unlikely event that rand returns int max, we'll get 1. Otherwise, rand over int max will always compute to 0. And for that reason, we need to cast either the numerator, which we're doing in this case, or the denominator to a double, or both. That just tells the compiler that we want floating point division. And regarding so I'll switch, is that enough on that? Yeah. Oh, so that's, the thing about the range is you want a random float in a range. So you take, let's think about it like this. Let's do this. Oops, random. What am I doing? Someone is editing my system. How could that be? That is so strange. It looked like I was hacked there for a moment. And did you see that?
Ileana Martinez, she's the one.
How did you get in here?
No, I'm just on your...
Oh, you're just like looking at it, right?
Yeah.
Yeah.
I can only read, I can't edit.
Oh. Oh, okay. So you're just reading. But we can see your cursor. We can see that you're looking. Okay. Yeah. Yeah. Can you? That's good. Try to delete something. Can you try to delete something? It'll refuse, right?
There she is again.
The hacker, you're now famous.
Bonus point.
You must have been inspired by that article I posted. So you can't delete, right? Okay, good. Thank you for checking that. Thank you. So we'll do a random from range. And we'll give the range here. And I'll use a double, not a float. And the double is double precision float. So we'll say from A to B. So we'll return a double. So we compute the double. Let's start by just looking at a number that's between 0 and 1. Let's just get that code to work. And I'm going to put this up here just to make it easier to read. Here we define the function random from range returns a double. It takes an interval A to B, so we want a random value between A and B. Right now we're returning a random value between 0 and 1. So we're not solving the problem 100%. We're going to do it step by step, one step at a time. So our first step is to produce a number between 0 and 1. And we'll see the random number generator here. Now some students do this. They put it in there. But that's a problem. Do you see why that's a problem? Why is it a problem to seed the random number generator inside this function? It's because every time we call the function, we seed the random number generator again. And what are we going to seed it to? Well, keep in mind, when this program runs, it'll probably finish in like a millisecond or less than a millisecond. So that means that time 0 will always return exactly the same value during the running of this program. So every time we call this function, we seed the random number generator with the same value over and over. That means we're going to get exactly the same number from rand. You see the problem? Because every time we seed the random number generator here, we're resetting that pseudo-random sequence back to its starting point. And we keep seeding it with exactly the same number. Because the program runs so fast, the number of seconds since 1970 isn't changing. So this is a common mistake that I see students make. So we should only seed it once. We only need to seed it once. So I like to do that right. I like to take care of that business right away before we do anything else. And then let's call this random from range. So we want to produce random numbers between the range 2.5 and 4.2. Well, right now it's behaving as if it's between 0 and 1. Okay. So let's take a look at that. Looks like we've got an error in there. Oh, this didn't make much sense, did it? I need to save, run again. 0.1589, 0.59. See, they're between 0 and 1. Now we want to get it to be between 2.5 and 4.2. I'm going to change this. I'll make it 4.7 or 3.7. Let's do that. It's easier to see it. So this gives us x here is a random number between 0 and 1. And we want a random number between a and b. So I've thought about this problem already, so I know how to do it. And the way I did it was I computed the range here. The range is b minus a. That's assuming that, you know, a is less than b. You know, we better check that with an assertion. A is less than b. Make it less than or equal to. See, this assertion, this line here, will fail if the condition being passed into assert is false. So that if you throw assertions into your program, you know, as you're making assumptions about the state of variables when your program runs, then it's good practice to put assertions in there that will fail in case your assumptions are wrong. So you can catch bugs that way. Now to use assert, we need it to include CAssert. There it is. We're going to be using this a lot in this class here, assert. So make sure you understand assert. It's very simple. If the expression passed into assert is false, the program will terminate and a line number will be reported right here. We'll see that it's in line 9, the program has halted because of a failed assertion. If the expression passed into assert is true, then nothing will happen. We'll just go on to the next statement. This is very useful. So we calculate the range. This is the distance between A and B. Yeah, question?
Yeah, instead of using an assert, can you use a if statement to catch it and then tell the user to put a number in that range? You
could do that, but here the user is not entering any number, so it wouldn't make sense here, right? But in the case that you're asking the user to input numbers, in that case, I would catch the data entry problem earlier in the code. And I would still put an assert in here, because this assert will test whether your validation code, the code that validates the user input, this assert will verify that your validation code is working correctly. So I'd still leave the assert in there. And by the way, what programmers do, these assertions can slow up the running of the code, although I think that's not important in most cases. But for programmers that are very conscious of time and shaving off clock ticks, in many situations, the assertions are omitted when you do what's called what do they call it? A production run, a release build. That's it. So you do a debug build, the assertions are active, but in a release build, like you're going to ship your video game, and you got thousands of checks in there. And you only want those checks to run while you're doing development because you don't want that extra overhead slowing things up. So you compile, you build your code in what's called a debug build. And then when you go to distribute the program to the customers, you do what's called a release build. And the release build will automatically omit all of those checks, the assertions and other checks that you have in there. So let's look here at this range here. So we got the range, B to A, right? Now think about it. When the number that you want is is the smallest value it's going to be is A, and the biggest value it's going to be is B. So it's, you know, it's A plus some number. That's, and X is in, you know, X is in AB. Oh, sorry, no, X is in 0 to range. That's what I meant to say. Put it in as a comment. Look at that. So A, that's this, you know, if the smallest value that X could be is 0. In that case, we return A plus 0, so we're returning A. That's the left side of the interval. The largest value that X could be is range. So that means we'll return A plus range. What's A plus range? A plus range is B. This range is B minus A. So A plus B minus A, that's just B. So we need to figure out how to get this, this X computed. How do we get X to be in this range, 0 to range? Well, look, this X here, this is between 0 and 1. So how do we get between 0 and range? It's, you just multiply by the range. Now X is between 0 and range. Does that make sense? You have to think about it, right? So let's take a look at that. It should be between 2.5 and 3.7. 2.8. 3.69. Look at that. That's a lucky one. That's almost at the top. 3.1. 2.5. It's working, right? You're convinced it's working. Well, that's how to do that one. And unit conversion, let me show you a little bit about this unit conversion here. So here the user inputs meters, and the program outputs the number of feet and inches that number of meters equals. And we round the inches to a whole number. Now I want people to keep working on that one. So what I'll do is I'll show you a related problem. Okay, we'll solve a similar problem. And then you can extrapolate from what I show you to the problem that you're working on. So the user is going to input something. Let's convert something to something, like maybe liters to cups and, what do they call it? Teaspoons? What should we do? Liters to gallons? So it should have two things. Huh? What do you think? Any suggestions? How about, I guess we'll do the liters. So how many liters? So we enter the liters, and then we input the liters. Liters. Did I spell that right? Liters. It's liters, right? Two T's.
I think that's right.
The first one is right? Wait a minute. You know, you're from that country over there with these leaders.
The one that's not American.
Yeah, that's right. Not from America. Right. Who else doesn't use leaders? Okay, so double leaders. There we go. Looks funny. I'm a bad speller, so you know. You guys are probably all playing a joke on me right now. All right, so I'm going to read the leaders, and we want to produce the number of what, gallons and cups? See? How's that? Let's produce the number of gallons and cups. So I'm going to take a look at my hint. Read meters into a double. Convert to integer inches. So we would convert to integer cups. Add 0.5 to round the result. So we're going to convert these liters into cups. Convert to integer inches. Read into a double, convert to integer inches. So that's an integer. So it's cups. It'll be total cups, by the way. So we're going to take liters. How do we convert liters to cups? Liters to cups. 1 liter. I spelled it. 4 point, whatever. 4.22676. So that produces cups out of liters. There's about 4 cups in a liter, so that sounds right to me. Now, this will, we're going to store the result in an int, so we're going to drop the floating point value. Then we're going to drop the fractional component. So we want to add 0.5 to round it before we truncate the decimal point from it. So that gives us total cups. And let's just see what that looks like. We're not done yet. Total cups. I'll do it like this. So we'll print cups. Okay, liters. So if I put in a 1, we should get how many cups?
4.2267.
No, but it's in cups is a total cups is an int. So we're rounding here. We want to round. 5. Well, that would be, well, you know, if you don't round, the total number of cups is going to be 4.22676, right? Which way would you round 4.22676? You wouldn't round that to 5. Huh?
4.
4. Should come out, should give us 4 cups, right? But see, we're confused there because we're adding 0.5. So isn't it going to give us, right? You see the problem there? But we're okay because we add 0.5, we're going to get 4.7. Remember, we're truncating, so we're going to get 4. You got to go over 5 to get 5. So there it is, 4 cups. Now, how many cups in a gallon? 16 or 64? I can never remember. Does anybody know?
16.
16 cups in a gallon. All right, so that means that we input 4 liters. We get something like 17 cups. Right? So we want the program to say, when we input 4 gallons, I'm sorry, 4 liters, we want the program to say 1 gallon, 1 cup, right? So we want 4 liters to produce 1 gallon, 16 cups, so 17 minus 6 gives us 1 cup left over. We pull out of 17 cups, we pull out 16 to get 1 gallon, and then we're left with 1 cup. So that's, did I ask for assertions here? Test that your program produces, okay. But I'm asking for, I didn't ask for test code, but I'll do that to show you what that is. So here's the test cases. And later I'll ask for test cases. So we'll do 1 liter equals 4 cups. 4 liters equals 1 gallon, 1 cup. You know, I'm not going to bother with the S there. I'm going to say gals and cups like that. Or gallons. And I know it doesn't read very well. So we have 2 test cases. So how are we going to get gallons? Well, gallons is going to be an integer. And then we're going to need cups, which is also an integer. And then we're going to print, let's just put some phony numbers in there. We'll put in 9 and 9. And then we're going to print gallons and followed by cups. Let's just see if the interface is working correctly. Put in 4 liters, we get 9 gallons and 9 cups. So you see how I'm doing this? I'm not just typing everything out. I'm actually I'm creating a sequence of runnable prototypes. This is called incremental development. I don't code for the final result. It's like golfing. You know, I mean, yeah, it's nice to get a hole in one, but you're focused just on getting the ball onto the green, onto the putting green, whatever they call it. And then you get close to the hole, and then you try to get the ball closer. You want to get it in there. It's nice to get it done in one shot, but that's very rare. So that's what we're doing. We're playing golf here. It's like incremental development, one step at a time. And we test it. Each step is a runnable version of the program. That's just one step closer to the solution. So now, how are we going to get the gallons out of this thing? Any suggestions? What's the formula? This is what we have. We got total cups, okay? And we got the other number that we have, which is important, is 16. There's 16 cups in a gallon. So what's the formula to compute the number of gallons that are found in total cups? Is anyone thinking?
Total cups divided by 4.
Total cups divided by 4. Because that would mean there's 4 cups in a gallon. So if the total cups, if we had 16 total cups, we get 16 divided by 4, we're going to get 4 gallons? That's not right, right? Use some examples. I'm using examples in my head. 16 cups 16 cups produces how many gallons?
One.
1. So the formula's got to produce 1 when total cups is 16. There we go. Everybody convinced about that one? And like, is this floating point division or integer division? Integer. So it's going to give us what we want. That's what we want. We want integer division. We're not rounding to gallons. How come we're not rounding to gallons?
Because we already included cups.
Yeah, we want the fractional part to go into cups. And we're going to round the cups. But we already did round the cups. All right, now, just think, let's suppose total cups, in your imagination, total cups is 17, okay? Then 17 divided by 16 gives us 1 gallon. What's the formula to compute the number of cups that are left over after we extract so many gallons? Huh?
The modulo.
Give me the formula.
It'd be like gallons modulo total cups.
Like that? Think about it in your head for a minute, okay? You got the number 17, all right? You pulled out 16 cups. How do you pull out 16 cups? In your head, out of 17. You're not using modulo, right? You're using subtraction. What was your?
Oh, I was going to say number of gallons times 16 minus cups, or cups minus gallons times 16.
What goes here?
Yeah, because if you had like... if you
Yeah,
had 17
what goes here?
cups, or total cups, sorry.
And like that, right?
Yeah.
What do people think? Like I got my total cup, I got 17 total cups. And we subtract 1 times 16. 17 minus 1 times 16. That gives us 1. That's good, right? Well, that's great. That sounds good, but let's do another test case. What happens if we had...
Shouldn't we add 0.5 to account for the rounding?
No, we already added it here when we
Oh,
computed total cups. We did our rounding in the beginning, and now we don't have to think about rounding anymore. And by the way, this is something I learned over several quarters to do it this way. I'm showing you the most efficient way to write this program because in the past, I presented a much more confusing solution. What's another test case? If we have 8 liters, how many gallons? It's going to be, what, 2 gallons, right? 2 gallons and either 1 or 2 cups. I mean, 2 or 3 cups, I think. Either 2 or 3, right? But, or 3 cups. Does this formula hold up with that other test case? If the user types in 8 liters, we're going to get a number, and it's going to give us, we're going to multiply by 4.22. What's 8 times 4.22? Oh, let's do it right here, right? This should be 8 liters. So 34 cups, because we're rounding. Our total cups is 34. So it'll be, 32 cups is 2 gallons, right? So you're left with 2 cups. Now, does this formula hold up? Total cups is 34. Well, what do we get for this line? 34 divided by 16 is what? 2. All right. So now gallons is 2. What's 2 times 16? That's 32. So 34 minus 32 gives us 2 cups. It works. The formula is good. You know, maybe. Let's check it. 8 liters, 2 gallons, and 2 cups. Look at that. 4 liters, 1 gallon, 1 cup. 1 liter. 4 cups? Yeah, that's right. Yeah.
But there's already a bug in it because if it's more than 16 cups left over, would it round over to liters or to gallons?
If there's 16 cups left over?
Yeah, because I had that with the conversion.
No, did you round up in the very beginning?
Oh, no. That's probably why.
That's the reason. That's why, see, I learned this lesson already.
Because I would have 0 feet and 12 inches.
Yeah, yeah, so that's the problem I had before in the past as well. So I just convert to integer total cups right in the beginning. That's the easiest way to solve the problem. Okay, so now you see how to solve this other problem. And that's how you do this one. All right, let's move on. Algorithms is the next assignment you need to do, and the course is really focused on your assignments. That's where you're going to learn, like programming on your own. And in the past, I used to show people the answers before they went into the lab or to work at home. I'm not going to do that now. You need to work on these. Detecting prime numbers, listing prime numbers, factoring numbers. This is the hard one, is factoring numbers. The code is small. It's tiny code. But to reason about it and come up with a solution takes some thinking. You'll use a while loop to do exercise 4. That's the easiest way to do exercise 4. Use a while loop. And you need to sit in a loop. So you're factoring a number like 100. 100 equals 2 times 2 times 5 times 5. Right? 2 times 5 is 10. 2 of those, that's 100. So when you get the number 100 or 120 or 1,000,000, whatever the number is, you've got to start pulling out factors. So you want to say, you start with a low number, like 2. You can start with 2. How many 2's can I divide out of the number? Well, then you're going to use modulo, right? Well, is the number evenly divisible by 2? If it is, then I'll divide out a 2. I'll print the 2, and then I'll divide out a 2 and reduce the number into half of its original size. Then I'll try 2 again. Maybe I can, in this case for 100, I can pull out 2 2's. So you want to keep trying 2 until you get to the point where you can't pull out any more 2's. So if you have 100 and you pull out 1 2, you reduce 100 to 50. You try to divide 50 by 2, it works. 50 mod 2 is 0. And so 2 divides 50. So let's pull a 2 out of 50. So now 50 shrinks to 25. Now, you already know in advance, as a human, that 2 won't go into 25. But then the code, your algorithm, the way you write it, you have to try to divide 2 into 25 with the modulo operator. You go 25 mod 2. Is that 0? No. 25 mod 2 is 1 because you got a 1 remainder. It's an odd number. So we printed 2 2's already. We've reduced the number to 25, and we're done. We pulled out as many 2's as we can. Now let's pull out as many 3's as we can. So what does the program do now? It takes 25 and does 25 mod 3. Is that 0? No, it's not 0. Well, that means 3 does not evenly divide 25. Let's try 4. Now, we're going to be sloppy about it. We could skip 4 because we already tried 2. 2 goes into 4. So we would have pulled a 4 out already because we already pulled out as many 2's as we could. So, in fact, we pulled a 4 out already. We pulled out 2 2's, so we're at 25. But for coding, to keep the code simple, we're going to try to divide 25 by 4. We go 25 mod 4. and we're going to get 1. Is that right? Yeah. So that's not 0. So we skip 4. Now we get to 5. 25 mod 5, that's 0. 25 mod 5 is 0. Oh, so we can divide a 5 out. So we take a 5 out of 25 and reduce it to 5. We try 5 mod 5, that's 0. Oh, then we'll take a 5 out of the 5, reduce the number to 1. Once we reduce the number to 1, we're finished. We terminate. We printed 2 2s, we printed 2 5s, we shrank the number down to 1, we're done. We terminate. That's how you solve this problem. But now how do you write code that detects whether a number is prime or not? So if a user enters in a number, some number, an integer, I'll say n. So, we're checking for primeness. So n, enter in an n. And then we're going to do something. And then we're going to have this, if prime, then we're going to print prime. Else, we'll print not prime. It'll look something like that. We're either going to print prime or not prime. We enter a number, 5, that should be prime. So we want to do something, we need to detect whether n is prime or not, and then we'll have some kind of condition. There's some condition there. We're going to either print prime or not prime. Yeah.
Can we use if-else statement?
Eval?
No, if-else. If-else
Oh,
statement.
if-else, yeah, you can use if-else, yeah. But not, that at some point you might need to use that, but actually I think the way to do it, you don't use if-else. Or you could. So what do you do to decide if the number is prime?
If the number is divided by 2, it's prime, right?
If you can divide the number by 2, then it's not prime.
Oh, sorry,
Yeah.
So,
Unless the number is 2 itself. 2 is prime. How do you decide, if you have some number n, how do you decide whether the number is prime or not? Let's take an example, okay?
All the numbers
5.
less than n have to be relatively prime to n?
Huh?
Like all the numbers below it can't divide n? They
That's-
share no common divisor?
Exactly. All of the numbers less than n should not divide into n. Then it's prime. If all of the numbers less than n cannot divide n, then n is prime. What does that mean? All the numbers less than n. Do you see a loop? You got to try 2, 3, 4, 5, all the way up to n minus 1. So you need a loop. And you got to try to divide all of the numbers less than n in this loop. You're going to try to divide all those numbers into n and see if the number evenly divides into n. So let's suppose you have a loop with I in there. Now I starts at 2, then it goes to 3, then it goes to 4, and it goes all the way up to n minus 1. How can you tell what's the code to decide if I evenly divides n? Yeah, modulo. N mod I. if I evenly divides n, what does n mod I equal? 0. So you're looking for a 0. So in your loop, you're trying to, using modulo with all the numbers less than n, if you find one that gives a 0, what do you know? You know that n is not prime. So you print not prime and quit. But if you try, how do you know when to print prime? Can you make the conclusion in your loop that n is prime inside the loop? Inside the loop, you can make a conclusion that n is not prime, because inside the loop, all you need to do is find one number that divides n. Once you find one, you can quit there on the spot, print not prime, and you're done. But in the loop, can you do the same thing for prime? Is there a state in the loop where you decide, oh, it must be prime. I'm going to quit on the spot and print, the words "you are prime." You can't do that in the loop because you got to try all the numbers. So you got to wait till the loop finishes. If you've tried all the numbers and you didn't quit, you didn't find a 0, then you can conclude that n is prime. All right, so it's a lot of talking there, right? Without seeing anything. Do some of you get it? How to do it? Okay. All right, so that's this exercise. It's focused on prime numbers and factoring. And the first exercise is just like user input. It's a guessing game. There's some secret number and the user has to guess the number. So I think you can get that one. So that is the third assignment. So if you haven't finished these, you want to work on both of these. If you can get all of these done, that's great. And then just to look forward really quickly, this is the exam. It's coming up. Arrays is the third assignment. Now, I suggest that you look ahead and do the later assignments as early as you can. So these are arrays. These are functions that have arrays in them. Let's see how many. There's 6 problems, all to do with arrays. And after this assignment, arrays, so we have arrays, algorithms, basics, and command line. Then exam 1 covers all of those topics. So the one thing that we haven't covered yet is arrays. So I wanted to talk about that today, get started on that. And here's the reading. I just modified that a bit here. Here's the lecture on arrays. Now last time I left the link here to overloads and templates. It's an advanced topic that we don't need to know in this class. So I'm not going to spend time on it. Maybe later I'll go back and we'll review that material. Maybe closer to the exam when we have time. And so here's the arrays. Here's the reading for arrays. An array is a sequence of values of all the same type. It shows a picture here. So the name of this array is called foo, and foo is a sequence. Actually, it's a container. So it's it's these contiguous storage locations. That's an array. A set of contiguous, side by side, touching each other. A set of contiguous storage locations. Intended all of the same size and intended to store values of the same type. So we can have an array of double, an array of string, an array of int, an array of char, whatever the array is, whatever data type is in there, they're all the same type. And look, these storage locations are numbered. The first storage location is labeled 0. And in this example, last storage location is numbered 4, labeled 4. And so we know that there are 5 slots because they start counting at 0, so it's the last valid, they call these indices, that's an index. These labels of these storage locations are called indices because an index is depends how you use it. In this case, an index is an integer value starting at 0. The last index is 1 less than the size of the array. And here's an example of a declaration. Here, foo is being the array, the name of this array is foo. It has 5, and this is showing a line here, int. So each of these slots holds an integer. So foo is an array of size 5 holding ints. And that's the declaration right there. Now, how do we initialize it? Well, here's one syntax to initialize an array. And so this shows how this statement produces this arrangement of numbers in memory. The first memory location, this, by the way, this is 4 bytes here. This int is taking up 4 bytes. So we've got a value of 16, in hardware, that's represented as a binary number. So that'll be in 4 bytes, followed by a 2, 77, and so on. It's the same, it's this from this initialization list here. And look at this. If we declare what Baz, I guess, Baz as an array of 5 integers, and we use this syntax, we don't put any numbers in the braces. Then the system will initialize Baz to zeros. Also, you can omit the size of the array. If you're going to provide this initialization code, you can omit the size of the array, and the compiler will create an array of size 5 for you here, in this case. You can also omit the equal sign. And this shows how to access a value. So in foo, these diagrams are good. So look at this expression here. We're storing 75 into position 2. So this is position 2 right here. This is position 0, position 1, position 2. Position 2 is the 3rd position. And if we want to put a 75 in here, we can use this syntax right there. This equal sign means assignment. This is an assignment operator in this context. We can read the value out of position 2 using this syntax. Now, foo2 is on the right-hand side of the assignment operator. Here, foo2 is on the left-hand side of the assignment operator. This statement reads the value in the 2nd position of foo and copies it into the memory that's identified with the variable x. When you work with arrays, you work with these loops a lot. So you see for loops in particular are very convenient when you work with arrays. So what we've been looking at are single-dimensional arrays, but there are also multi-dimensional arrays. Here's a 2-dimensional array. Jimmy. Here, Jimmy is 3 rows by 5 columns. So this is what you might visualize it looking like. 3 rows of 5 columns. in memory, memory is sequential. So actually this data, although it looks like it's a table here, in memory, it occupies a sequence of locations. So first is the first row, followed by the second row, followed by the third row. That's how it's laid out in memory. By the way, you could also lay it out like column-wise. You could lay out the first column, followed by the second column, followed by the third column. But that's not how it's done. It's laid out row-wise, I think. I'm pretty sure. Here's an array that has more than 2 dimensions. So here we're declaring an array, Jimmy, which is 3 by 5, 3 rows of 5 columns. And this is how we identify this particular cell. See this cell? It's in row 1, column 3. And so we use this syntax here. Let's see what this is. This has to do with how memory is laid out. And let's skip over that. Arrays as parameters. That means passing an array into a function. Parameter means a value that's passed in to a function. You have a parameter list. When you call a function, you pass in data into it. Let's see an example. Like here, print array. Here's an example of a function. And this function, this is the argument list for the function right there. And then we just started talking about functions. This function print array has 2 arguments. The arguments are separated by commas in a parameter list or argument list. And the first parameter has the name arg. All the other information around it talks about its type. The braces here, or the brackets, mean that it's an array, and the int here means it's an array of int. So arg is an array of int. That's the first parameter. The second parameter has the name length, and that's of type int. So the type precedes the name of the object. So here we're using arg. Here we're using the first parameter, or first argument. Here we're using length, which is the second argument or parameter. And I think that's enough. I don't need to talk any more about that. I think it's pretty straightforward. There's some exceptional things like this is a for loop that iterates through an array A. And this is a syntax that has been used in other languages, but not C++. And this syntax you'll need to compile under C++ 11. So it's a new addition to the language. But this, like I said, this syntax exists in other languages, like for instance, JavaScript. This has been around JavaScript for a long time. Even though JavaScript is a newer language. So C++ is an old language. So you've got newer languages that came after it that fixes problems and provides conveniences that the older languages didn't have. So now C++ is slowly coming around to adding those features into itself. And I don't know if it's really making things easier, because I don't see a lot of C++ code that looks like that. Well, I don't look at a lot of C++ code anyway, but I would be surprised if this is, well, you'll see a lot of existing code. That's the thing about the language C++, there's a lot of existing code that was written a long time ago. and it uses an older version of the language, so you won't see these kind of expressions in it. So if you go to add new code, what do? Are you consistent with the existing code base and make things look the same, or do you start migrating your code to new forms that are coming out with new versions of the language? I don't have an answer for that. That's a question. That's a decision that you would have to make in that situation. These multi-dimensional arrays, because they have rows and columns, you'll see nested for loops to process the elements. So if you want to look at every element in a two-dimensional array, you'll need to have probably a nested for loop like this. So this top for loop iterates through the rows, and the for loop within it iterates through the columns. So each row, you look at all the columns. Then you go to the next row, and then look at all the columns. And the next row, and then look at all the columns. That's how that works. And finally, this is an advanced topic, that there is, in the old version of the language, the standard library didn't have an array, but that's been added recently. It may exist prior to C++ 11, I'm not sure. We can test that actually. I'll just put that right in here. Include array. This is a new feature. And what happened? This file requires compiler and library support for C++ 11. So we needed to use --std equals C++ 11. It still isn't working. We have some, oh, the bug isn't here, right? All this stuff. So this is just junk. There we go. If I leave this out, then we get the error. So this feature is in C++ 11, and it makes the array. So I won't talk about it because we're kind of out of time here. And but you can store that away and maybe look at it later. Any questions? Okay, that's it then.